unknown is theta 1. So we can get the value of theta 1. So this is how we get the theta 1 value. And we can also check P1x and P1z. So P1x and P1z over here is here, this one, and this one. So now we already know the theta 1 value, so this will be all known values. So because C1 we know, Px, Py we know, sine y we know, and A1 also is a known value, and also here. So both these are known values, and if we check the other side, on the other side, P1x is this, and P1y is this, like this. So if we write it, we can get something like this. And then we can use R sine by C3, their plus together is L. So we can get the length of L. And by just adjusting, and so we can get the theta 3. So inverse kinematics is basically you can just verify and find whether you can eliminate other variables and only left one variables. So you can use arctangent or arccosine to find the value. And usually if we have cosine, then we'll use, if we have cosine theta equals to something, then we'll have sine theta equals to 1 minus cosine squared. And together we can use arctangent. So normally if we use numerical to do the mathematical calculations, we usually use arctangent. So we already get the theta 1 and theta 3. Now we can see in this form. So we continue to times another T2 minus 1 and T3 minus 1. Also T2, 3 minus 1, T2 minus 1. So it's cancelled out. O is also equal to identical matrix. So it will give you an equation like this one. And on the left, we can just multiply and give you these 12 equations. And on the right, also give you another 12 equations. So we're still like finding the relationship between these 12 equations, and then we can see if you find take P3x and P3z. P3x is over here, P3z is over here. So P3x is here. And you can see, since that we already know theta 1 and theta 3, so we already know two values, and this is the only unknown. We already know two values. So 2, 3, and 1, 1, 1, 2, 3, 3, 3. So here we can get the theta 2 and theta 2 plus theta 3. So together we write the two equations over here, and we can give you cosine theta 2 plus theta 3 is equal to this. So all these are known values, and also we can get the sine theta 2 and theta 3. And we use arctangent, we can get theta 2 plus theta 3. And we just minus the theta 3 we get in the earlier slide, then we can get theta 2. So this is how we find the theta 2. And we can also see, now we already know theta 1 to 3. So now we can see AZ1. here. A1Z is over here, so it's over here is these are known values. I'm sorry for that. I think it's should be A3Z. So it's cosine. Here is equal to cosine theta phi, and here are all known values. So we can get theta phi. So we already have theta 1, theta 2, theta 3, and theta 5. So only two left. So if we see these equations, on the left part, all these we already know the values. So we only need to find, like you can use cosine theta 4 and sine theta 5, because we already know theta 5, then we can find theta 4. And also you can see this one is sine theta 5 and sine theta 6. We already know theta 5, so we can find theta 6. So if you only left two unknowns, it's very easy to find the relationship. So you can just find two equations randomly, or then you can solve the theta 4 and theta 5. So this is just use all the equations to solve the inverse. And the another method I want to talk about today is using the geometric structure of the robot to solve the inverse kinematics. So if you are very familiar with the symbols and matrices, you can use the previous method. But if you are not really comfortable with all these matrices or the symbolic form, then maybe you can try using the geometric structure method to solve the inverse. So if we see on the top view, this is a line, and this is the rotation. The first joint, the rotation joint. So if our robots move the first joint over here, so if we see these 2 points, the only joints that can affect this angle is only theta 1, the joint 1, can affect this angle. So if you still remember, we can separate a robotic arm into a arm part and a wrist part. So it is like if you see on the top view, maybe the robotic arm will be like this one. So this point is here. It's the wrist part. And the first joint is over here. So if you see from this point to here, the only joint that can affect this rotation is joint 1. Because joint 2 only affect in this direction, so it affects the length of this line, this point, the distance of this point. And for joint 3, it's also rotation in this direction, so it's also affect the length. So you can see the joint 2 and joint 3. It can only affect the distance, but not the rotation. And 4, it's rotating aligned with this robot arm, so it cannot affect the rotation. And then we get to joint 5. So this is the joint 5 position. So in total, the only joint that can affect this rotation is only joint 1. So if we can find the line vector of here and here, then we can get the theta 1. This is how we get. So in the last, I think the lecture slides, we have already get this. We also draw this figure to show that's how we can compute. So the first thing we need to do is we want to find the position of joint 5. So the joint 5 is like this, and this is joint 6. And here is joint 4, if you remember. So here we have the any factor. So now we need to refer to our frames, which we set earlier. Our Z6 is in this direction. So your joint directions, your toward the any vector directions, the Z is always pointing. It's the same direction as this direction. And we know that from the P5 to our tool, here is 100 millimeter. And this point is Px, Py, and Pz. And we know this direction, and the length is 100 millimeters. So we can calculate back to this position. So this position, P5, will be equal to P5x, P5y, and P5z. And it is equal to Px, Py, Pz, and minus 100. And we want to know this direction. And this direction will be your z direction. So if you see your rotation matrix, this is the direction of x, this is direction of y, and this is direction of z. So it's minus 100 ax and ay and az. So you can, through this, you can get your P5 position. Is it okay? And now we get our P5 position. It's over here. And we need to project it onto our XY plane, because we know that our theta y is on the XY plane. So if we project it down to our XY plane, then we can have the length. So if you see from the top view, from this view, so here we have already have the P5x and P5y, the coordinates. And the length over here will be Pfx squared plus Pfy squared. And square root. And if we see the, so this is from the base frame. And here have another 150 length. If we see carefully, see this figure. This is the rotation. Okay, so we don't have this one. The rotation is over here. Okay, so rotation is over here. Okay, so it's okay. So here the length is P5x squared plus this one, and we can call it R. So the projection over here, this length is R. And then another one we need to find is the so if we see from the top view, so this is the base frame, so it's y0 and x0, and assume that we have this point is P5x and P5y. And if we get the length here is P5x squared plus P5y squared. And we can just use the P5x or P5y or P5x, and we can get the theta 1. So just through the very basic trigonometry, and we can get the value. And for the theta 2 and theta 3, since that we already know from this point, so this point is we already know this R, the length. So the length from the, or we can call it L. So we define the length from the base frame, the center, to our P5 center is L. And because we know that there is, here is 525, and here is 150. So this is the point, the joint 2. Here we have joint 2, and here is joint 5. Here's joint 2. So here is the base. And we know this, here is P5x, P5y, P5p. So this is from the side view, and this is from the top view. And so the P5 525 is in the direction of V, and 150 is in the direction of you need to times the x and times the theta 1. So here we only get our theta 1, so we can also find this point. So this point is 150 times cosine theta 1, and 150 times sine theta 1, and 525. So if we find the distance between these two, and we can get the length of L. And this is the length of L, and this is the link 2 and link 3. So it will form a triangle. So from this triangle, then we can get, this one is the length of your second link, and then also your length of your third link. So you can say it's here is 770, and this is 100 plus 740 squared, or we can call it L. So we can use the law of cosine, so we can find this angle. And we find this angle, then we can find, and also through this one, because we know the L, then we can find this theta 2. And using the law of cosine, then we can find theta 2. So this is through the geometric, then you can find your theta 1, theta 2, and theta 3. And this one, I think we have the this is the 2D robots, which is we have in the slide. You can just follow the same procedure to solve. So after we have theta 1, theta 2, and theta 3, then we only left 4, 5, 6. And for 4, 5, 6, we will come back using this, because we already solved all the left parts, and we only left the right parts. So if you use the geometric solve to solve the theta 1, theta 2, and theta 3, all these will be a known value. So the only variables will be left in all this. And it's very easy to, so here you can find theta 5. If once you find theta 5, you can find theta 6 and theta 4. So this is how you solve it.
In the slides that you upload, there isn't the slide included.
Yeah, because everyone's because this is based on how you set up your conventions. So I only left the where you can find the sentence parts, because since if your convention is different from the slide, then your DH parameter will be different, and then your flow kinematics will be different, then all the equation will be different. Yeah, and actually, to be honest, this one is different from this one.
Oh.
Yeah, because this one is when I solve during my master homework, and then the first frame I set is over here. So there should be have something different from. Yeah, so that's why I just cross out. I just afraid that you will be misunderstood. Yeah, okay. But the procedure and all the process will be the same. So if you are not familiar with to find all these, to dealing with all these equations, you can just think about using the geometric. I think that for you can just think this is, so actually this one is all the same with our practical. If you still remember our practical setup, is we have joint 1, and then up here we have joint 2 and joint 3. So it is all the same with the practical. So this is, you can just solve by geometry and you can get it. And for the wrist parts, then the easier one is you use this equation, because since we already know these 3 variables, so and this is the given matrix. So this is all known values. You don't need to really calculate the equation, because you already know the theta 1, theta 2, and theta 3. You can just substitute all the known value into it. Then you already know all the values. So only variable is over here. Then you can see it's very easy. Yeah. So the easier way may be trying using the geometric structure to solve the first 3 angles, then use the equation to solve the wrist part. Yeah. And here we want to introduce a toolbox. This is a robotic toolbox from NetApp. and you can use it to verify your design. So it's by Peter Koch. So he is a very, I will say, maybe very famous professor in robotics. And so he developed this toolbox, and it's open source, and it's on his website, so everyone can download it. And you also have a book. I think it's several books. So on his website to teach you how to do this toolbox. Use this toolbox. So inside the toolbox, you can find the rotation. So every function, it has a very visualizations, because I know sometimes it's very hard to visualize how the robot moves or how the rotation moves. So like the rotation, here we have the visualization, and also a transformation matrix, trajectory. And for the robot, you can create a model. So create a model, you can use the DH parameters to create your own robots. And also there have some samples or some examples inside, like this one is Puma 560. And I think we also have the found-up robot inside the toolbox. And you can also show animation, forward kinematics, inverse, Jacobian, and inverse dynamic and forward dynamic. And I think these two we haven't covered. And also we have some like mobile, so like some navigation method like SLAM and all the robotics applications. And the last three will be doing meta plugin called Simulink. So I think some of you are very familiar with it. So if you open the toolbox, then you can see here, you can create a model, then you can set in the input, the target, this one is the target's position, and you solve the computer joint space trajectory, or you want to calculate the inverse kinematics or calculate the forward kinematics. It can all done within this toolbox. So you also can set up your DH parameters. So like this one is the P5, the Puma 560, and here is the DH table defined. So here are some properties. So these are the simple robots, and you can also create your own robots. And that's all for today's lecture. So any questions for today? Okay, then we'll be continuing with our final project. So today is 21st of October, and we'll announce the final projects. And on the 11th November, you will give a proposal. So every group needs to submit a paper report and doing our presentation for your project proposals. So basically, is what is the methodology you are aiming to solve your projects, and also how you want to design your robots. And on 25th is final exam, so it is, we only have one exam. And so this exam we only covering from the sensors, but that's all introduction parts, and to the Jacobian, which we have already taught last week. So basically, if you already know the forward kinematics, inverse kinematics, and the Jacobian, how to calculate Jacobian, then you will be fine with the exam. And we only have the problems in our slides. So you will not find like very hard robots to want you to calculate the kinematics. And then we have 1 week of progress discussions. And then on 12/09, is a particle competition. So you'll bring your robot to the class, and we'll have some mission to do a particle test. And on the last week is the final presentation. So is there a question about the schedule? Yeah.
Do we by any chance get all the exams so we can prepare for it?
You mean the mock exams? Or?
Yeah, like mock exams or all the exams. Because we usually get all the exams in Germany, so I don't know if that's a thing here.
Okay.
I guess not, it's fine.
I can give you some revised topics, so our question will be within these topics.
Okay,
Yeah.
that's fine.
And these are the list of items we'll give you on maybe on next week, because we already sent out, but still haven't get all these items. So this is the PCA 96885, and also this one, and the Arduino Uno, and batteries, and 4 motors, and also a battery box, and wires, and the linkage. After you have already designed and done your linkage design, then you can come to our lab to use the 3D printer, or you have your 3D printers in your own labs, then it's all fine. And so the objective of this project is you need to build a 4 degree of freedom robotic arm. So, and you complete 3 given missions. So you simulate and validate the design. So it is really the same as we have already done all the practical stuff. And the score will be presentation 35%, so paper report 25%, methodology 20%. So the real mission implement is 10%. So we will have some score about the real mission, but very, very less, because all this is 40% out of your full score, so 10% is already 4 months. It's only 4 months. So it's very, very, so it's what we want. You not really want to like scoring really high, but it's, this is not the only intention. Yeah. So our intention is you can have some creativities, and you can think of missions. Is there any design, very, very creative design to solve all these missions? Because since we only have 4 degrees of freedom, so it was, so if you want to have very creative ideas, you need to think about it. So you'll have a group to discuss with your teammates. So this is the assigned mission. We have 3 stages. The first stage is we have 2 circles. So your robot should be fixed or grabs a pen at its any vector position and finish the task. Here is the place you can place your robot, and we have 3 stages. So the area is 20 centimeters times 20 centimeters square. So you need to make sure that your robot can fit into this area. And there's 2 position pins for your position reference. And then for the first task, as there are 2 target circles on different heights. So you need to touch the first circle and get open the wall, and touch the second circle and back and forth for 5 times. And it's focused on the accuracy and repeatability and how to calibrate with the robot arm. So because the motors is only feed-forward motors, that means that you cannot get the sensors feedback. So you are allowed to, if you want to implement other sensors. But usually we are checking if you didn't implement any sensor feedback, then you can do your calibration done very well, then that will be a very, very good idea. And the second one is there's a slope, and here we have two A point to B point, and there have a curve. So you need to start from the A point and draw it into a B point. So while drawing, do not exceed the area, but if you exceed it, it's never mind. So the only thing is you need to complete. So you can also like doing this one if you don't want to do this. So, but there are some penalties, and so it's try to analyze the curve function and control the robot to do the curve functions. And the mission 3, here we have 16 pillars over here, and during before your test, we will just randomly remove like 4 pillars to have your robots, you can do the path planning. So we will randomly remove the pillars. So you need to do the path planning. And the rating, this is the final score, and we have a base score times your complete percentage, and because we are encouraged to finish the task, so there will be a reward. That's if you finish the task, then you can get more marks. And there's a penalty if you validate the rural areas, like, for example, if you comes back and you did not get into a circle, or you didn't get over the wall, so we're just encouraged to finish the task. Then, if you can finish the task, then you can try for more accuracy. And there's some, so this is error happen times, then we'll have some penalties over here. So is there any questions? And we'll give you the CAD model of this mission. So you can simulate in your, whether you want to simulate in some software, or you can just use the calculation and you can do and we'll bring this platform, I think, after your final exam, so you can test it. So first thing is that you need to discuss with your teammates what is the design of your robots, because you have 4 motors, and so this is like one configuration is like this one, and you can just add the 4th one over here, but there's some shortage. So how you want to arrange your robots, and is there any arrangement that's very suitable for this task? So this will be something you need to discuss with your teammates. And after you already done your design, then you need to calculate some the kinematics modeling of the robots, and make sure that you already know how to get to the list, like these 2 points, and doing the curve and doing the path planning. So any questions? Okay. So that's all for today. Yeah. And if you have other questions, you can ask me. And thank you.